that paves my way to discover myself and to witness the world moving forward in technology. I want to go to a place that sets a futuristic pattern of education filled with ideas and radical performances. Basically, I want to live my dream.
Dayanand Sagar University. Live the dream.
I want to change the world by doing something new for them. It's like everything in this whole world requires something which needs a software or a program that needs to run on. So I'll make sure that everything has a program. I'll make it work like whatever way it needs to be or the better it wants.
The sessions are all very interactive with little bit of lecturing followed by a lot of group discussion and work amongst the students so they can answer the questions that are posed by the lecturer. So that is one thing that makes our teaching learning process unique.
I did my engineering project which has taken me somewhere beyond. I can represent it anywhere all over the world. So like that it has given me so much of knowledge. Even right now if I come to the department for any help and they really help me out with my research work or anything. So it's been that support, that motivation from the department, it's still there.
When I entered, I was just an average student here. The teaching helped me in such a way that at the final semester I became the topper.
When I was coming from G in that business environment, I was very skeptic about how it's going to be here. But the way they have set up the entire lab and the kind of equipment which is available here, it is second to none. And their work, according to my mentor who's in GE, which is an industry, he claims that the work done in DSI and worldwide is renowned, and their lab work is renowned across labs, be it Stanford, be it Europe, ETH Zurich, or be it Australia.
We use the lesson management system called Moodle together with Piazza. So all our lecture notes, we develop it ourselves, we put it online. Students have access to all this online material which they can download at any time, and they also have access to a question and answer forum where a shy student who would otherwise not ask a question can get on this question and answer forum and
A very good morning to one and all. Welcome to the second day of the 5th International Conference on Intelligent Computing and Communication, Icicc 2021, organized by Department of Computer Science and Engineering, School of Engineering, Dayanand Sagar University. Myself, Assistant Professor Shraddha Naik, Assistant Professor Tina Babu, and Assistant Professor Vaidehi Verma from the Department of Computer Science and Engineering would like to take this opportunity to extend a warm welcome to all our delegates, research scholars, faculties, and participants. After successfully organizing 4 back-to-back international conferences, Springer is delighted to showcase your research talent and welcomes your participation in the 5th International Conference on Intelligent Computing and Communication at Dayanand Sagar University, School of Engineering. Icicc 2021 is organized to provide a platform for academicians, researchers, scientists, professionals, and students to share their knowledge and expertise in the field of intelligent computing, communication, and convergence, and address various issues to increase awareness of technological innovations and to identify challenges and opportunities for the development of smart cities using multidisciplinary research techniques. The aim of this conference is to present a unified platform for advanced and multidisciplinary research towards design of smart computing and informatics. The theme on a broader front focuses on various innovation paradigms in system knowledge, intelligence, and sustainability that may be applied to provide realistic solutions to varied problems in society, environment, and industries. The scope is also extended towards the deployment of emerging computational and knowledge transfer approaches, optimizing solutions in varied disciplines of science, technology, and healthcare. Research is saying what everybody else has seen and thinking what nobody else has thought. With this insightful thought, it gives me immense pleasure to share that all the eminent speakers and guests from different areas of expertise had joined us today to share their knowledge and vast experience with the research community. Now, we will move towards the keynote address session. Over to you, Professor Tina.
Good morning, everyone. It's indeed a great pleasure to introduce our esteemed keynote speaker, Dr. Karthik Gopalan, Professor in Computer Science at Bingham University, US. Associate Editor of IEEE Transactions on Cloud Computing, to address the session on the topic titled From Nesting to Bare Metal, Strange Adventures in the Virtual World. Dr. Karthik Gopalan is a professor in computer science at the Bingham University. He received a PhD from Stony Brook University, MS from Indian Institute of Technology, Madras, and BE from Delhi Institute of Technology. At Bingham University, he heads the Operating Systems and Network Group, where he enjoys working with highly talented group of students on the cool new ways to build and use virtual machines, containers, and hypervisors. Some recent projects include virtualization for bare metal cloud, live replacement of hypervisors, live migration, and privacy-preserving virtual machines. He is a recipient of National Science Foundation Career Award and Watson School Recognition Award for outstanding research achievement. He serves as an associate editor in IEEE Transactions on Cloud Computing. He has authored over 70 publications and received 12 US patents. Before joining Bingham University, he was faculty at Florida State University, lead architect and developer at Rether Networks Incorporation, and senior software engineer at Wipro Global Research and Development. I would like to request Dr. Karthik Gopalan to deliver the keynote address on From Nesting to Bare Metal, Strange Adventure in the Virtual World. Sir, please.
Hello everyone, welcome to this talk. I'm Karthik Gopalan, Professor of Computer Science at Binghamton University. I'd like to begin by thanking Vice Chancellor K.N.B. Murthy and Dr. Rajesh TM for inviting me to give this keynote talk. So this talk is about virtualization and how it is related to the cloud computing environment in the modern digital age. Both cloud computing and virtualization are essential for the modern cloud digital infrastructure. So I will talk about two different projects at two different ends of the virtualization spectrum, nested virtualization and bare metal. So this is a joint work with a number of student co-authors and industry collaborators, without whose hard work this research would not have been possible. So I'd like to begin by stating two obvious maxims for computer science researchers. They're kind of a little bit of funny maxims that every problem in computer science can be solved by one more layer of indirection. You can take any standard component of an operating system, for example, virtual memory or file systems. These all represent the principle of adding one more layer of indirection to solve some problem of abstraction or multiplexing. So, and likewise, every time we add another layer of indirection, then we get to the second maxim, which is that we open up another optimization problem. So indirection introduces overheads into the system design. And as a result of that, CS researchers can get busy solving, reducing the overhead and optimizing it out of the way. So virtualization particularly, which I'm going to talk about today, provides opportunities both for introducing indirection and for solving these overhead optimization problems. Let's get going. So I'll give a brief background about what we mean by virtualization, particularly in this context of a talk. It's a very broad topic by itself. So I'm going to narrow down the scope of the kind of virtualization we are talking about. So this picture here shows a traditional operating system. And we have hardware devices, which is the machine with CPU, memory, IO devices, and so on. And on top of that, we have the traditional operating system that directly controls the hardware. And it provides an abstracted view of the hardware to all the applications that run on top of the operating system. So there are a number of processes that are running on top of this operating system. So from there, we go to an environment where we have virtual machines. And what that means is that we still have a hardware as before, but instead of having an operating system as the first layer of software controlling the hardware, now we have another layer of software called the hypervisor. The hypervisor is also known as an operating system for operating systems. So hypervisor now controls the hardware, but instead of running just one operating system environment, it can now run multiple virtual machines, and each virtual machine runs its own copy of operating system. These operating system instances could be different, for example, Windows and Linux, or they could be the same. For example, you could be running multiple instances of Linux operating system side by side. So this is very widely used model. All our cloud computing platforms, for example, have hypervisor layer, and on top of which they run virtual machines that belong to various customers, right? So there are many benefits of virtualization like this. For example, you get the benefits of isolation among customers. One customer doesn't know that virtual machines from another customer is running besides the same, besides that customer on the same physical machine. And you also get flexibility. Hypervisor can now do certain things, for example, introspection or implement some network monitoring policies and so forth. So this hypervisor, this another layer of indirection, provides a rich layer where you can implement a lot of different features. From there, we are not satisfied with one layer of indirection as CS researchers. So we say, all right, what if we had another layer of indirection? And this brings us to this somewhat not fully explored area of nested virtualization. So what does that mean? We again have a hardware layer, and on top of this, we run something called a layer 0 hypervisor. And what is this layer 0 hypervisor? It's a hypervisor for hypervisors. So what's the purpose of doing something like that? Essentially, we have two virtual machines here running VMA and VMB, and there could be more. And within each virtual machine, we have an independent hypervisor that's executing. And within those hypervisors, we have virtual machines running. And those virtual machines have their own copies of operating system. Nested virtualization is often useful, for example, in development environments where you're developing a hypervisor, and for that to test and debug, you need a virtualized environment to run the hypervisor. Or it can also be used for various other purposes like security and so forth, where you want to have a hypervisor that implements antivirus protection or introspection or network monitoring, and another commodity hypervisor that provides full multiplexing capabilities and so forth. So this is kind of a brief introduction to what traditional operating systems, system virtual machines, and nested virtual machines mean in our context. So with this in mind, now we're going to look at two projects that we have explored in our research group. One is span virtualization, which uses nested virtualization or nesting for a multi-feature cloud infrastructure. And the second one is direct visor, which is the opposite end of the spectrum, where we do the optimization problem, which is that we try to eliminate the overheads of virtualization for something called a bare metal cloud. So I'm going to discuss each of these projects one at a time and give you some taste of what kind of research issues we might run into them. So the first project is called span virtualization. This is based on 3 papers, primarily the Usenix 2017 paper, but also a couple of use case papers from VE 2019 and 2016. And so let's get going and see what it's about. So originally, when hypervisors were designed, as I mentioned earlier, hypervisors are operating systems for operating systems. And this is not really a new concept. Like back in 1970s, IBM mainframe systems had hypervisors, virtualization fully supported. So, and these have, with cloud computing, virtualization has had kind of a rejuvenation and renewed interest, and it has kind of become a backbone of the cloud infrastructure. So what are hypervisors? Hypervisors were originally conceived as a thin software layer that remains transparent to the virtual machines that are running on top of it. So what that means is that hypervisors should have very little footprint, execution footprint, and memory footprint, and so forth. And they should not be visible to the guest operating system and applications that are running within them. So it was also supposed to be a secure layer because of the property that it's very thin, meaning that it's running very little code. It has a very small trusted computing base. So as a result of it, smaller trusted computing base means that they're more secure, more trustworthy, and so forth. That was the ideal world. That's how hypervisors started. But soon people found this additional layer of indirection provided a nice place for them to add more features. So this brings us to the modern hypervisor model, which is that now hypervisors don't just provide virtualization of the hardware, but they also carry a lot of different services for the virtual machines that they're running. For example, hypervisors implement a number of features, such as live VM migration, checkpointing, taking snapshots of VMs that are running. You have fault tolerance, high availability services. If a VM fails at one end, then you have a copy of it ready to take over on another machine. There are other features such as live guest patching, network monitoring. You can transparently monitor the network activity of these virtual machines from the outside without having to insert any code into the VM. So it's very similar to introspection, meaning that you examine the code and the binaries that are running within the VM without having to install any tools such as antivirus tools or malware detection tools inside the VM. So as a result of this addition of features into modern hypervisors, hypervisors have become very big and fat, meaning that their trusted computing base has increased. They're almost as complex as traditional operating systems. In fact, hypervisors are often built into existing commodity operating systems. So they essentially have the full feature set and the full set of vulnerabilities that come with traditional operating systems. So instead of being thin and nice and secure, now they are fat, and of course they're feature rich, which is a good thing, but they're not as secure anymore, right? So what we would ideally like is take these services out of the hypervisor, but still allow the VMs to benefit from these services. So this is where our idea called span virtualization comes in. So here what we do is that we use nested virtualization to separate out the features from the traditional hypervisor. So what does that mean? In this picture, we have a traditional thin hypervisor, the layer 0 hypervisor, and on top of it at layer 1, we have several other hypervisors running. These we call feature visors. So A, B, C, and D, these are feature visors. They provide different features. So for example, one could be providing network monitoring, another could be providing VM introspection, the third one could be providing a specialized storage virtualization service, and so forth. And on top of this, at layer 2, we have virtual machines running. Now, what's special about these virtual machines compared to traditional nested virtual machines is that these VMs can be controlled by multiple layer 1 hypervisors. And this is kind of a new idea in the sense that traditionally each VM is supposed to be controlled by only one hypervisor. But now we are saying no, a VM can be controlled by multiple hypervisors. I'll explain in a little bit what that means. But in this example, for example, VM1, it possibly starts out as being controlled by the layer 0 hypervisor, but once it needs additional features, then we can sort of slide in layer 1 hypervisor, the hypervisor A, underneath VM1. And then at some point we can slide in hypervisor B underneath VM1. So what this means is that both the layer 0 hypervisor and hypervisor A and hypervisor B, all three of them are simultaneously controlling the virtual machine and providing it with services. So, so what we call this is a multi-hypervisor virtual machine. So one virtual machine that's running on top of multiple co-located hypervisors. So each hypervisor would control one or more resources, for example, CPU, memory, or IO devices for the virtual machine. And they also collaborate with each other. They can't do their own thing separately. Sometimes they have to talk to each other and collaborate in order to control the virtual machine. And likewise, you can have many such virtual machines running side by side. Each of them could be a multi-hypervisor virtual machine. So the goal of the span virtualization project is twofold. One is that in order to implement this, we don't want to rewrite the entire virtual machine and its software and so forth. This mechanism should work transparently. We should be able to take any commodity virtual machine, run it on top of this span virtualization platform, and it should be able to run without changes. So that's the first goal. The second one is service isolation. What that means is that although here hypervisor A and hypervisor B are controlling the same virtual machine VM1, but they should not be aware of each other, right? So we don't want untrusting third parties, although they are controlling the same VM, but we don't want them to interact with each other for safety, security reasons, for more compartmentalization of services. So as a result of this, this leads us to a design that I'm going to describe in the next few slides. And as we show, we can obtain both guest transparency and service isolation. So this is a high-level picture of what span virtualization does. It's what its architecture looks like. In the layer 0 hypervisor, we have a few things. First, we have, of course, the traditional functions of memory management, IO management, and so forth. But in addition to that, we have certain coordination mechanisms to talk to layer 1 hypervisor. So here we are showing that a span guest or layer 2 virtual machine, it can, of course, be controlled by a layer 0 hypervisor, but in addition, it's being controlled by several layer 1 hypervisors at the same time. And they have, these layer 1 hypervisors are able to request the layer 0 hypervisor to attach or detach from being able to control the span virtual machine. So for example, one of these hypervisors may say, I want to control the CPU scheduling. Another one could say, I want to control memory management. The third one could say, I want to control storage virtualization for this virtual machine. So, and in addition, they can subscribe to certain events. For example, memory trap events or IO request events and so forth. So L0 hypervisor acts as a event processing unit, which means that it either relays events from one L1 hypervisor to another L1 hypervisor, or it emulates certain features related to the span guest. So the resources that we are considering here are virtual CPUs, or as they call it, vCPUs. Each span guest may have one or more virtual CPUs that need to be scheduled, just like normal processes are scheduled by traditional operating systems. Hypervisors end up scheduling virtual CPUs. We also have various types of virtual resources: virtual CPU, virtual IO devices, and of course, pseudo physical memory of the guest. What that means is a virtualized view of the physical memory made available to the virtual machine. So, control and sharing of these resources between various L1 hypervisors has to be coordinated by the L0 or the lowest level hypervisor. So now we will look at each of the virtualization for each of these individual resources. So first we start with memory. Here we are comparing the memory virtualization in a traditional single level virtual machine, a nested virtual machine, and in our case, span virtualization. For a traditional single level virtual machine, there are two levels of address translation involved. When a virtual machine, within a virtual machine, a process accesses a memory location, the hardware would consult a page table for that virtual machine, and then it would translate that to something called a guest physical address. And the guest physical address would then be further translated by the memory management unit, or the MMU. And to do that, there will be an EPT, or extended page table, that translates a guest physical address to a host physical address. When we go to nested virtualization case, there's one more level of indirection. What that means is that a virtual address would be translated to a guest physical address, which then must be translated to the hypervisor's view of its physical address, or the L1 physical address, which is then translated to the host physical address. Now, the problem is that the MMU has only two page tables. One is the first level page table, and the second is the extended page table. But nested virtualization needs another page table, which is the virtual EPT in this case. So since it doesn't have that, the MMU can't understand 3 levels of translation. So what the nested virtualization designers did was they played a trick. So what they construct is something called a shadow EPT. Shadow EPT is kind of a combination or a compaction of virtual EPT and hypervisor's own EPT together. So you can take the translation from one and the translation from another, resolve it and stick it into the shadow EPT. So the shadow EPT is what is seen by the memory management unit in the hardware. So in effect, we get virtual address to guest physical address, and then through the shadow EPT, we get a host physical address translation. So and this seems to work fine. For with sufficient optimizations, you can make a regular nested virtual machine work with this kind of memory address translation mechanism. When we go to span virtualization, we kind of make this problem even more complex, because now there's not just one L1 hypervisor, there are many L1 hypervisors that are controlling the same L2 virtual machine. So in order to deal with that, of course, we have multiple shadow EPTs that must be constructed, and they must all be kept in sync with each other by the L0 hypervisor. So, and that's what we end up doing. So in the L0 hypervisor, we have multiple L1s that control a common guest, and each of them has a shadow EPT, but the entries in those shadow EPTs must all be kept in sync, so that irrespective of which hypervisor is controlling the guest, we get appropriate or correct memory mappings during the execution of the VM. But this is kind of showing a more pictorial view of what I described in the previous slide. In there's the L0 hypervisor that maintains a bunch of shadow EPTs plus the EPTs for L1 hypervisor, and there is a span guest that has its own virtual address for each process it's running, plus the page tables that it maintains, and a bunch of L1 hypervisors that communicate the updates of the virtual EPT and the shadow EPTs with each other through the L0 hypervisor. And the various L1 hypervisors, they can subscribe to memory events from L0. For example, if one with the span guest performs some write operations on a memory region through one of the hypervisors that controls its CPU, then the other hypervisors that are, for example, controlling the IO devices may need to know that certain memory region has been updated. So they may need to catch those updates and update their own virtual EPT mappings. So I won't describe all of these details here in this talk, but feel free to refer to the paper. So next I will describe the IO virtualization for span VMs. So the first figure here shows a traditional IO device emulation for span VMs. So there is this usually a split device driver model. What that means is that inside the virtual machine or the guest, there is a front-end device driver, which then communicates with the back-end device driver, which is located in the hypervisor. And there's usually a shared memory ring buffer that allows the front end and the back end to talk to each other. And the guest can put IO requests into the ring buffer, and the hypervisor can put IO responses into the ring buffer. So this works fairly well for virtual IO devices, but when we split the control of the CPU and the IO device control among multiple L1s, then we have to make them talk to each other. So what that means is, so in this example, we have the VM which is still controlling the front end, but here's L1A which is controlling the back end of the IO device driver. But there's L1B which may be controlling the virtual CPUs of the span VM. So as a result, we have to forward any IO interrupts through L1B, and any responses, any event notifications back from the vCPUs to the IO device through L0 back to L1A. This adds some additional overheads, but for most purposes, this works fairly well in the prototype that we have developed. So these were really the two major challenges: maintaining a consistent memory mapping and getting IO virtualization to work correctly. So we were able to implement all of this in a prototype system using Linux and KVM based virtualization. We use the KVM hypervisor, and I'm going to just talk briefly about 3 use cases of off-span virtualization. The first one here shows a network monitoring and VM introspection services that are simultaneously controlling a span VM. So at the window down at the bottom right, you see that there is a virtual machine, and this virtual machine is infected by a malware. So in this case, there's a KBeast malware that we injected into the virtual machine. So once we start the malware, then if you look at the list of processes, it won't show that process in the process list because the malware hides itself from the list of processes. But on the other hand, we have an L1B, one of the L1 hypervisors that controls this VM, that's running an introspection tool called volatility. And what volatility can do is, it takes a dump of the memory image, and it can scan the memory image of the VM, and it can find all the processes. Even if they are hidden inside the VM, they can be seen outside of the VM. So in this example, we take a dump, and there we see that the evil process, the malware, can be clearly seen. At the same time, though, so that by itself is not the new thing. What we are doing simultaneously is that there's another hypervisor, L1A, which is simultaneously doing network monitoring. So it's monitoring the network IO activity of this hypervisor. And as you can see, it's a simple TCP dump command that's monitoring the network. And the novel thing about it is that this network monitoring feature and the VM introspection feature, they can be run side by side on the same VM, same guest, and independently of each other. So these are 2 different services that are operating on the same VM. And if you can kind of take out one of these services or plug in another service anytime during the VM's execution. So that's the really cool aspect about this mechanism. So this is one example. The other one is a situation where we can update a hypervisor on the fly. What that means is that we can treat span virtualization as a mechanism where we have a thin L0 hypervisor, which we call a hyperplexer. And the purpose of the hyperplexer is not to do any real virtualization, but to just swap in and swap out layer 1 hypervisor. So we have a VM that's running. It was running on top of an old L1 hypervisor. And at some point, we all need to do feature upgrades or apply patches, security patches, and so forth. And this can be very disruptive. Normally, to apply operating system level updates, we have to shut down the operating system and so forth. But here, with our mechanism, what we can do is we can sort of pull out the old hypervisor and slide in a new hypervisor. We simply call it attach and detach operations. So first we will attach a new hypervisor, which remains dormant, and then we detach the old hypervisor, at which point the guest control is transferred to the new hypervisor. And this can be done completely transparently. This is a live operation, meaning that the guest is running during this time all the time. So again, this is a use case for the mechanisms that I just described. And we have shown that it can have very low disruption on the guest. So only around 70 milliseconds of guest down. A third case is something called ephemeral virtualization, where normally a guest would run on a regular hypervisor, but sometimes, occasionally, it may need to use certain services. So what we call a feature visor. The old way was doing this was to use full nested virtualization, which is shown in figure B. You'd have a hyperplexer, a feature visor, and then a virtual machine. But with our model, now we can have, we can sort of do this nesting when we need to do it. What that means is that we have a hyperplexer and a VM runs normally, but occasionally, for example, when we want to do VM introspection, we would transfer control of the VM to this feature visor. It's like an attach operation that we saw for span virtualization. And once we have done provided whatever feature we wanted to provide to the VM, then we could relinquish control of the VM back to the hyperplexer, right? So if this gaining control and relinquishing control operations are really quick, then the VM won't notice the difference, and we are able to provide the benefits of nesting, benefits of having these feature visors without having their overheads, right? So the trick is to make this transfer very quick, and the way we do it is through a very fast memory co-mapping mechanism that is described in the paper, which is really the key for everything that I'm describing here. A very fast memory sharing and co-mapping mechanism among multiple hypervisors, right? So these were the three use cases, and kind of wraps up our discussion of span virtualization. There are additional performance numbers that I didn't really mention here, but there are overheads, but they're reasonable limits for a first prototype like this. But at least we have shown as a proof of concept that span virtualization is possible, and it is practical and useful most of all. So with that in mind, now we're going to shift gears and move to the other end of the virtualization spectrum, which is bare metal virtualization for bare metal cloud computing. So what does this mean? As I mentioned briefly earlier, we want to run VMs, but with as close to bare metal performance as possible. But we also want to retain the benefits of virtualization. So this was a paper published in VE 2020, and I will very briefly describe how we went about doing this. Usually in a multi-tenant cloud computing setting, there are various VMs running side by side. So I have my VM running, and then some other customers' VM running, and so forth. And I don't know who these other customers are whose workload is running besides in the same physical machine as my own. So there's a huge security issue, trust issue, the possibility of side channel attacks, and so forth. So what happened was customers started asking, especially enterprise customers with critical workloads, they started asking for dedicated physical machines. They wanted to run dedicated physical machines in which only their workload runs and nobody else's workload. And cloud providers, of course, provided something called bare metal cloud. They could provide customers, allow customers to run on dedicated physical machines, and at the same time guarantee that there will be no other tenants on that physical machine. So the problem with that was that there were no hypervisors that could do things like VM migration or network monitoring. All those features we were discussing earlier, those features were not possible. So we get bare metal performance, but we don't get the benefits of virtualization. So in this project, we thought, how about providing the benefits of bare metal as well as benefits of traditional virtualization. So we developed this system called Direct Visor, which is like a very thin hypervisor that you can sort of slide in under a VM when you need it, but then remove it when you don't need it. So what we do is we run these VMs called direct VMs that have mostly direct access to the hardware, and what that usually means is there are pass-through IO devices that are widely used in the industry already. So that's not the new aspect, but in addition, you could provide dedicated physical CPUs to the virtual machine. But there is one aspect where there is a problem, which is in timer interrupt handling. Like normally, timer interrupts are very critical for bare metal performance. for achieving low latency. So, so in our case, we sort of figured out how we can provide direct timer interrupt delivery to these virtual machines. So, so that's kind of the summary. We provide dedicated CPU, memory, and I/O, but most importantly, we provide direct timer interrupts and also direct interprocessor interrupts. One virtual CPU can send an interprocessor interrupt or IPI to another virtual CPU without any intervention of the hypervisor. But besides these, in addition to being able to do this, we also retain the manageability benefits of virtualization. What that means is we are able to retain traditional services like live migration, introspection, and so forth. We can still do that. There's still a hypervisor, but it stays dormant most of the time. When you need to run some features that are there in the hypervisor, then you can trigger it and run it with very low overheads. So I'll just briefly mention what these direct timer interrupts and IPIs mean. So we use a feature called posted interrupts to provide direct timer interrupt injection mechanism. Traditionally, like shown in figure A, you have indirect injection. What that means is there's usually a local advanced programmable interrupt controller, or LAPIC, which injects timer interrupts into a virtual machine. But in order to deliver these timer interrupts, there's usually a hypervisor that traps these interrupts, and then it emulates their delivery. There are a number of steps involved in this timer interrupt injection. I won't go into all the details here, but the point is to show that there is significant overhead involved in getting the timer interrupt from the hardware on each CPU from the LAPIC on each CPU to the guest operating system, which needs the interrupt. So what we did was on x86 CPUs, there is a new feature called posted interrupt, which was introduced a few years ago. And this was usually reserved for IO devices, for PCIe IO devices. And we figured out a way to use this mechanism to deliver timer interrupts directly to the guest OS. So instead of having these whole bunch of steps before we can deliver an interrupt into the guest OS, we could now use the posted interrupt mechanism to deliver a timer interrupt directly into the guest OS. So, and we can do the same thing for interprocessor interrupts. Earlier, the hypervisor would have to emulate the delivery of interprocessor interrupts between virtual CPUs of the same machine. But now we can do direct IPI delivery. And we do it with really low latency. That's very quite comparable to the bare metal timer interrupt latencies. The other aspect was manageability, and a big part of manageability is live migration. We designed the previous mechanism in such a way that we can turn it on and off. So it's a direct access to IPIs and timer interrupts. These could be turned on or turned off as and when needed. So for example, if we have to move a VM from one physical machine to another, we could turn it off, switch to normal virtualization where everything is emulated, live migrate the VM to another machine, and then turn it back on at the destination machine. And this is really important because this was one of the big drawbacks of the traditional bare metal clouds, where you lost all these manageability capabilities when you rented machines from these guys. So, but now you can have a hypervisor that provides live migration and also direct hardware access. And we were able to show that we can do this with extremely low latency. The live migration of direct VMs has very comparable performance to the live migration of normal VMs, which is, if depending on the size of the VM, it could be a few tens of milliseconds to a few hundred milliseconds of downtime. Again, there are a lot of details in the paper on how we implement this mechanism for direct VMs, live migration mechanism for direct VMs, taking into account direct hardware access to network interface cards, timers, IPIs, and so forth. So here are some performance numbers. Since performance here is the main criteria for success, the a green line here shows a cumulative distribution of the latency that we observe for timer interrupt for a specific benchmark called cyclic test. And we implemented our own version of this to get more accuracy at the kernel level. So normally you can see that there's a wide distribution of latencies, but somewhere around 9.2 microseconds is very common latency for traditional vanilla fully emulated VMs. And then for bare metal without any virtualization, you get a timer latency of around 1.51 microseconds. With our direct VM mechanism, what we call direct interrupt injection, we get a timer latency of around 2 microseconds, which is very close to bare metal. There are still some overheads involved, but it's mostly related to the poster interrupt mechanism itself. Pretty much we get rid of all other emulation overheads with our mechanism. Likewise, here we see IPI latency, where we bring it down from 9.35 microseconds down to almost 3 microseconds. So in summary, I've spoken about two projects at two ends of the virtualization spectrum. In one case, we implement something called a span virtualization, where we support a single VM that's controlled by multiple hypervisors at the same time. And in order to do this, we use nested virtualization. And we found that, of course, it's very hard to get nested virtualization right. But once we do that, it also opens up many possibilities. You can provide a lot of different services, such as VM monitoring, introspection, the live hypervisor replacement, ephemeral virtualization, and so forth. And the other aspect was towards the bare metal virtualization end of the spectrum, where we implemented a project called DirectVisor, where we provide performance that's close to bare metal for virtual machines, but we also retain the traditional manageability benefits for traditional clouds. This brings us to the end of this talk. If you have any further questions, feel free to contact me at this email address. Thank you all for listening and have a good day.
Thank you, sir, for sharing such insightful and enriching knowledge with us.
Now, moving on to our next keynote speaker's technical talk, I would like to take this opportunity to welcome and introduce our next keynote speaker, Dr. Govindrasu Manimaran, Professor of Electrical and Computer Engineering at the Iowa State University, US, who will be addressing the session on the topic, Cybersecurity for Critical Infrastructure in the Information Age. Dr. Govindrasu Manimaran
Sorry for the interruption. We'll be just holding for a few minutes as our next keynote speaker has not yet joined. So I kindly request you to have patience for a few more minutes. Thank you.
change the world by doing something new for them. It's like everything in this whole world requires something which needs a software or a program that needs to run on. So I'll make sure that everything has a program. I'll make it work like whatever way it needs to be or the better it wants.
The sessions are all very interactive with little bit of lecturing followed by a lot of group discussion and work amongst the students so they can answer the questions that are posed by the lecturer. So that is one thing that makes our teaching learning process unique.
I did my engineering project, which has taken me somewhere beyond. I can represent it anywhere all over the world. So like that, it has given me so much of knowledge. Even right now, if I come to the department for any help, and they really help me out with my research work or anything. So it's been that support, that motivation from the department, it's still there.
When I entered, I was just an average student here. The teaching helped me in such a way that at the final semester, I became the topper.
When I was coming from G in that business environment, I was very skeptic about how it's going to be here. But the way they have set up the entire lab and the kind of equipment which is available here, it is second to none. And their work, according to my mentor who's in GE, which is an industry, he claims that the work done in DSI and worldwide is renowned, and their lab work is renowned across labs, be it Stanford, be it Europe, ETH Zurich, or be it Australia.
We use the lesson management system called Moodle together with Piazza. So all our lecture notes, we develop it ourselves, we put it online. Students have access to all this online material, which they can download at any time. And they also have access to a question and answer forum, where a shy student who would otherwise not ask a question can get on this question and answer forum and pose a question which can be answered by all his fellow students or by the teacher also.
If you had asked me to talk like this in the first day when I joined, I would have straight away said no, because I was too afraid, I was too scared. But it gave me that confidence. They pushed me through everything, and the main thing is they built confidence that who I am now.
We seem to have this twin campus framework of the hospital, of engineering, of pharmacy, of nursing, all on one single campus, and that makes for a very interactive and challenging environment. Students, faculty can engage with one another on this campus and bring together a product that is more comprehensive in nature. So that to me symbolizes well-rounded research. That would be, I think, a flagship for research in the area of biomedical engineering.
Autodesk partners with Dynasavy University to offer unique proposition to students, professionals, innovators, and maker communities to foster innovation and to translate their ideas into reality. And they're going to do this by having access to cutting-edge technology and mentorship from experts from industry and from an academia standpoint.
DSU, as we can say, it is industry on campus, and it is one of the establishing center with collaboration in leaders of industry like Robert Bosch Rexroth India Limited, Autodesk, and National Instruments.
The entire college, the greenery makes you just anytime happy.
You won't get this kind of atmosphere in any other college, being so peaceful, having lots of friends from very different branches and being connected to them, playing games, doing software, having a competitive spirit between us.
At the coming batch, I would like to say that it's just that they need not constrain themselves from doing anything. They just have to be there and part of it, and they'll come out in flying colors.
Dayanand Sagar University. Live the dream.
It's already late. Where's Arjun?
He's looking for universities, right? Maybe he's held up there.
You look so tense. By the way, did you get to choose the university?
No, I'm unable to find a university that meets my requirements.
Whoa. Meet your requirements? What exactly are you looking for?
I'm looking for a place that gives me an opportunity to grow, to excel, to invent, and to innovate. I want to be a part of an institution that paves my way to discover myself and to witness the world moving forward in technology. I want to go to a place that sets a futuristic pattern of education filled with ideas and radical performances. Basically, I want to live my dream.
Dayanand Sagar University. Live the dream.
I would like to take this opportunity to welcome and introduce our next keynote speaker, Dr. Govindrasu Manimaran, Professor of Electrical and Computer Engineering at the Iowa State University, US, who will be addressing the session on the topic Cybersecurity for Critical Infrastructure in the Information Age. Dr. Manimaran holds BE in Computer Science and Engineering from Bharati Dasan University, 1989, MTech in Computer Technology from the Indian Institute of Technology, 1993, and PhD in Computer Science and Engineering from the Indian Institute of Technology, 1998. He was named Fellow of the Institute of Electrical and Electronics Engineering, IEEE, in 2015 for contribution to security of power grids. May I now request Sir to kindly deliver the keynote address on cybersecurity for the critical infrastructure in the information age. Please, sir.
Good morning, everyone. Can you hear me? Hello, can you hear me?
Yes, sir. Yes, sir. Good morning, sir.
Okay, thank you. Yeah, good morning. My name is Manimaran Govindarasu. Thanks for the introduction. I'm going to, before introducing the topic, first of all, I would like to thank the organizers for giving me this opportunity to make this presentation. I believe it is very important. The subject matter that is being pursued, the title of the conference and various sessions, they are very, very important in the current research context. I really applaud the effort that has gone in over the years, and also especially during this pandemic, still able to run this conference in a virtual format. With that, again, I would like to thank the Vice Chancellor and organizers, everyone, for giving me this opportunity. With that, let me get into my lecture. This is about cybersecurity for critical infrastructures in the information age. I'm a faculty member in the Department of Electrical and Computer Engineering at Iowa State University. So I work in this area for a while. I'm going to talk about some critical infrastructures, in particular the energy infrastructure. This was mentioned in yesterday's inaugural session also, different critical infrastructures, machine learning and intelligence analytics, cybersecurity, data privacy, different topics were briefly discussed by different speakers, including Internet of Things and analytics in that context. My presentation today kind of relates to those presentation in a way, focusing on the cybersecurity aspect. So this is the agenda. So I'm going to sort of introduce what is critical infrastructure. We all know it, but just to give you an idea and what are the cyber threats and some of the attack vectors, then going on to providing a cybersecurity framework. Broadly, it's applicable whether it is energy infrastructure or transportation or advanced manufacturing, doesn't really matter. Broadly, this kind of framework is useful. Then I will briefly talk about some components of that framework, including like cyber risk assessment, and then cyber physical system security aspect, focusing on smart grid. Then another case study, cyber security for smart agriculture. Then finally, make some concluding remarks. So if you see here, critical infrastructure sectors as defined by the US CISA, that is Cybersecurity and Infrastructure Security Agency. This is an agency within Department of Homeland Security in the United States. They have identified 16 critical infrastructure sectors. As you see at the bottom, there are 16 critical infrastructure sectors whose assets, systems, and networks, whether physical or virtual, are considered so vital to the United States that their incapacitation or destruction would have a debilitating effect on security, national economic security, national public health or safety, or any combination thereof. It's an exact verbatim from CISA website. It's essentially applicable to any nation, whether India or other countries. There are critical infrastructure. They are so vital for the national security and economic vitality. They must be protected. As you see from this particular chart on the top, communication, critical manufacturing, energy infrastructures, food and agriculture, healthcare, information technology, you name it, like transportation sector, all are critical infrastructure. The important thing is many of these critical infrastructures, they are cyber physical. That means there are a lot of physical assets that are there, like energy infrastructure, generation, transmission, distribution. These are physical infrastructure. On top of that, cyber infrastructure is embedded for monitoring, control, and various operations of the physical infrastructure itself. So in other words, these are cyber physical infrastructures. There are many other things like government, for example, or financial. Those are not cyber physical, but there are a lot of cyber and operational issues that come into play. But essentially, when you look at cyber physical infrastructure, they are sort of interconnected. There is interdependencies between cyber or critical infrastructure in general. So one needs to not only understand each infrastructure sector, security, resiliency, privacy issues within that sector, but also the interdependencies between infrastructure is also an important issue that needs to be understood as a nation, as a smart city or smart whatever you call it, whichever level, at the city level or state level or national level, this needs to be taken into account. Just to give an idea, power grid or smart grid, and conventionally it used to be called power grid as a physical infrastructure. The modern view is it's a cyber physical infrastructure, it's a critical infrastructure, it's a smart grid. So as you see at the diagram shown at the bottom, this is from NIST framework that was developed several years ago that sets the sort of motion for smart grid initiative. Smart grid initiative led to other kind of smart things everywhere, no smart transportation, smart manufacturing, smart cities, all kinds of things. So what you see is there are a lot of physical thing, generation, transmission, distribution, those are physical infrastructure. Then what you see, those dashed line, I mean not dashed, solid lines, those are basically communication infrastructure, and the market, operation, service providers, all those things what you see, those things provide essentially monitoring and control function for the physical infrastructure. If something happens on the communication or something happens on the any of the cyber, whether it is a sensor or control center or communication channel, that will have serious consequence on the physical infrastructure, like creating outage, blackout, or equipment damage, expensive equipment like generators or transformer getting damaged, and so on. Or major regional blackout, or for that matter, it could be national blackout. Such thing can be caused by cyber incident on the cyber infrastructure, which is embedded into the physical infrastructure of the modern grid. More and more automation happening in the power grid sector, many other sector, manufacturing, transportation, everywhere, to make them smart. More digitization, more cyber elements are being introduced. Although they provide a lot of benefit in terms of efficiency, in terms of achieving higher resiliency and other economic benefits, but they also introduces a lot of vulnerabilities. The cyber attack surface expands exponentially with the introduction of newer sensors, newer communication models, newer analytics, newer decision-making logic, and so on. So introduction of IT technologies are great from one viewpoint. From a cybersecurity point, they introduce attack surface. So it's not necessarily we should not introduce them, but we need to introduce them in a more responsible way, in a more secure manner. That is the essence of any research when you talk about cybersecurity for critical infrastructure. So this slide simply gives you an idea. So what are the different different attack vectors that are possible? Probably a lot of, these are all common things that is already known. So for example, the protocols that are employed in these systems, they could be targeted, social engineering, spear phishing, those kind of things. That is a very common form of cyber attack. Intrusion of different types, ransomware, malware of different types, spyware, those are all other target. Denial of service attacks, insider threats. So there are different class of attacks that are possible targeting critical infrastructure, like some of them listed here, like energy infrastructure, water distribution, transportation, and so on. So the number of attacks on these infrastructures keep growing, both in numbers and also in sophistication. What you see here, the Industrial Control System CERT report from the Department of Homeland Security in the US, 2015 report, they also have subsequent reports, 2016, even later reports. Just to show an idea, on the left, what you see is different critical infrastructure sectors, how many incidents that actually happened. Critical manufacturing, energy, transportation, those are some of the dominant ones in that particular report. So what simply shows is these are many incidents that were reported in that year, only a period of time. On the right, what it shows is different type of vulnerabilities that were exploited in these infrastructures. 110, they couldn't classify one way or other, but you see the spear phishing, that is a common form of exploitation, sending some email with an attachment or some sort of links that a user by accidentally or inadvertently they open the file or click a link, causing malware to be downloaded. These are typical form of spear phishing type of attack. Then there are other type of things, weak authentication, access control violations. There are a lot of such things also have been reported. So the point I want to convey from here, pretty much all the critical infrastructures, predominant one being energy, manufacturing, transportation, they are being targeted, and there are different flavors of attack. Most of them belong to the spear phishing, but there are other things, weak authentication, they're technology based, there are human error based, and so on. There has to be a holistic approach for cybersecurity. So this is again to illustrate some of the incidents that have happened in the energy infrastructure. On the right, if you see the Stuxnet worm attack that targeted uranium enrichment facilities in Iran in 2010. That is a major attack. It is a first reported cyber physical attack on critical infrastructure. Then subsequently, cyber attack on the Ukrainian power grid in 2015, again in 2016. Then there are several other incidents on gas pipeline network or petroleum refinery and so on all over the world, different parts of the world, including the recent one, Colonial Pipeline ransomware attack, targeting the IT infrastructure associated with the Colonial Pipeline infrastructure in 2021. So this number of the frequency and sophistication of these attacks keep growing, and it's really a serious concern. Compared to a decade ago, yeah, it is a random thing. It may happen, may not happen, but the adversaries are becoming more and more sophisticated, and more such incidents are happening. So one needs to be very vigilant and pay attention to those things and make sure those infrastructures are protected against this attack. So this is just to give an idea what is the threat landscape, and this threat landscape is not static, it is dynamic. It keeps evolving year by year. As I mentioned, adversaries are becoming more and more sophisticated. The types of attacks are also having significant consequences. So what you see is one way to look at. This was a report published by US Department of Energy and North American Electric Reliability Corporation. Jointly, this report was published several years ago, but it kind of gives you a broad outline about different events. What is the likelihood in the y-axis? What are the consequences? It's a risk assessment kind of approach to look at what is the cyber security for this kind of infrastructure. So, I mean, any critical infrastructure for that matter, but this was primarily targeted or designed for energy infrastructure. So if you see in the middle now, the probing, like somebody probing your network or device, a very common thing, the likelihood is very common, but the consequence is very little. So it may not have any impact, but people are scanning the network for some vulnerabilities. Like in the middle somewhere, denial of service attack, yeah, it may happen, little less common, but still it's very likely. The consequences, there could be consequences as well. Then the worm and other things, and then distributed denial of service attack. Then you go to the top right, you see poisoned attack. That means the data itself is poisoned, or data integrity attack, some measurement or control, they are being compromised, that will have malfunction in the underlying physical process of the critical infrastructure, causing major incidents like blackout and so on. And if you see on the y-axis, the different types of adversaries, less structured, simple, like cyber kiddies, they want to just try to attempt something. Then directed, more structured attacks, somebody wants to gain monetary gain, like for example the Colonial Pipeline attack, those kind of thing, you can put it more like a structured attack. Then the topmost, which is more like highly structured, the advanced persistent threat type of attack, where the major attacks happen due to nation state actors targeting in a more strategic way. Advanced persistent threat comes in that form. That means there is no immediate need, but they will be slowly looking for opportunity patiently and look for the most opportune time to strike to cause the maximum damage. So that is typically the nation states. It could be due to whatever warfare or to gain supremacy or things of that nature. So the idea is, as you see from this chart, likelihood of different actors injecting different types of attacks, what would be the consequence from less to severe. So we don't want the system or any of those, when you do, when you multiply the likelihood of event times consequence, that is the risk. So the important thing is one has to do risk assessment to understand whether the risk is acceptable or not. You can't completely say there is zero risk for my system. There are some risk, but the risk, whether it is acceptable or not. If it is acceptable, we don't need to worry about. If it is not acceptable, then those risks have to be mitigated. So anything that goes into from a yellow zone to red zone, that means red zone means those risks are above the acceptable threshold that needs to be attended to. So again, depending upon the company profile, one can have this kind of risk assessment, or as a regional network, one could have risk assessment. Even as a national level, one could have risk assessment. So that is understanding everything from a risk perspective is extremely important, especially when it comes to cybersecurity research perspective. Then the next one is, okay, there are a lot of research that has been going on for decades in information technology area, IT security. Can we just use them for the OT? OT is the operational technology or industrial control system, SCADA or cyber physical system, those kind of contexts. The challenge is the operational technology, they are somewhat unique. They many times use legacy protocol. They have limited resources in terms of computing, communication, memory, and other kind of resources. So one cannot use heavyweight cryptographic solutions into the OT environment. That may be a limiting factor. So limited encryption capability, poor patch management. There are a lot of software bugs. Many of those systems were designed just a performance in mind, not security in mind. The security was not even design infrastructure. So just retrofitting those legacy infrastructure with IT security is not practically feasible. So one needs to come up with better way, a tailored solution that is important. So then even if the channel is encrypted, those encrypted channels can be tampered using denial of service or timing attacks, because this industrial control system, they are sensitive to timing. There is an underlying physical process. It's a control system. Even small perturbation in timing properties can impact the underlying physical process from a stability perspective, from a efficiency perspective, from a reliable operation perspective. So timing attack, denial of service attack, replay attack, that means even if the channel is encrypted, the adversary may not know what the actual content, but they can keep replaying a same packet again and again, stale packets, whether it is a measurement packet or control packet, it can have impact. So then the coordinated attack, multiple elements are compromised simultaneously to maximize the impact in terms of consequence. Then insider threat, somebody knows the internal operation of the system, they want to turn against those infrastructures. Those are all need to be addressed. So what I want to convey here, just to having simple IT security, just to having encryption, those are good starting point, but they are not sufficient for providing security for cyber physical infrastructure. Then the third reason is the vulnerability and threat landscape keeps evolving. Like for example, you may have a platform, legacy platform, perfectly fine. Tomorrow there may be a new vulnerability. Even Windows and other platforms that are there, new vulnerabilities, zero-day exploit, and other things keep coming up. Then malware, ransomware. So these are all evolving scenarios. So just thinking about cybersecurity as a sort of oh, there is a goal. Yes, it's a goal, but it's a journey. It's not you reach a goal. One has to keep sort of improving your system, keep assessing the risk, and it's an ongoing process. That's why one has to think beyond IT security. So from a solution perspective, the framework which I mentioned, one way to look at the framework, so what you have is there is sort of 6 stages. The similar kind of framework you may have seen, but this is published in Proceedings of the IEEE that is listed at the bottom several years ago. But it's broadly applicable to any critical infrastructure. One is deterrence. Can you prevent the number of attacks or the occurrence of attacks happening itself? Deterrence is extremely important, but many times deterrence is more of a policy, or I would say more treaties, and those things can help to reduce the attack, or they can achieve deterrence. It is less of a technical issue. It's more of a political and sort of treaty, international organization working together and come up with an agreement or treaty of that kind. So there are a lot of policy aspect involved. Then you can try to minimize that, but many times, minimize the attacks. Many times the adversaries are not nation states. It could be, somebody, hacker group and others. They target system. They don't necessarily follow any international laws or any convention or any treaty. So not every attack is you can't really deter in those cases. And even with among countries also, there are not many international treaties exist. There are attempts are being made, but not many exist. So attacks are definitely likely, and it's happening. So then what do? The prevention. Can we prevent those occurrence of those attacks? That's where the risk assessment, risk mitigation, and various techniques to reduce the attack surface. As I mentioned, the attack surface keeps expanding with the introduction of digitization in this infrastructure. How do you sort of analyze the attack surface and systematically reduce the attack surface? Various techniques, you have firewalls and all kinds of authentication. Every solution that is typically used in the IT infrastructure, they could be leveraged, taking into account the limited power, limited resource capability of this OT infrastructure. So prevention is one solution, but prevention, every attack may not be preventable. As I mentioned, zero-day exploit, or even everything may look fine, but it is stealthy type of attack which manipulates very critical control or measurements that will have impact. Everything appear to be normal, the firewall and other authentication, everything appears to be normal, but still the attack is possible. So then you have detection. Can you detect online those attacks? That is the next important thing. So again, intrusion detection, signature-based intrusion detection, then more advanced machine learning-based, data-driven, which is machine learning-based anomaly detection, or things like model-based anomaly detection. There are techniques hybrid of model and data-driven anomaly detection approaches are there to detect stealthy attack vectors, that is online detection. In real time, one should be able to detect those attacks. If those attacks are detected, what are the ways those attacks are mitigated? That's where model-based mitigation, the physical system model is understood, the underlying physical characteristics of the control system is understood, like the grid, the physics of the grid is understood, based on which what is suitable actions. Most of the model-based system relies on that. So it may not be the most efficient way of mitigating, but keeping the system in a stable operating condition, even if it loses the optimality, that is perfect, still it's okay. So there are a lot of mitigation measures based on the model. That's what they work on. And they also rely on some data-driven approach using ML, machine learning kind of algorithms. Then the resiliency, if there are major attacks or faults or fault plus attacks happen, how do you keep the grid or keep the infrastructure operational, regaining the operational status even if it was sort of disrupted for some time. So resilience is extremely important. Then the final thing is attribution. Attribution is more like a post-mortem analysis to see who are the actual perpetrators of the attack, where it originated, which country or which machine, which host, tracing all the way back to the origin of the attack. This attack attribution is extremely important. If attack attribution technology is there, in fact, that itself can serve as a deterrence. Many times, if you have a capability to sort of pinpoint out where it is coming from, and you have a capability and tools, that adversary will think twice before even launch an attack because they will be caught. So attribution could serve as a sort of preventive mechanism or as a deterrence itself. So essentially deterrence, prevention, detection, mitigation, resiliency, and attribution all are important. There are a lot of things what you see on this chart on the top: enabling technologies, cloud computing, software defined networking. Those are all important to achieve some of those things what I mentioned. Whether anomaly detection, mitigation, forensics, all those things. Data sets and models, they are extremely important, especially when you talk about test beds and you want to develop accurate anomaly detection and other things, data sets to train the model. Those are all extremely important. Then at the bottom, what you see, there is also analytical tools or science of security. One could use game theory type of tools, mathematical tools for doing risk assessment. There are techniques like moving target defense. You keep confuse the adversary so that they don't get a perspective of how the system operates. Then there are other kind of things, as I mentioned, machine learning. Those things are very, very useful. So there is a lot of research that can go on in this area when we think about bringing different technologies and different analytical tools that are out there to solve this comprehensive problem from a life cycle perspective. How do we deter, prevent, detect, mitigate, and keep the system resilient, and do some forensic analysis? So on the left, what you see, this whole ecosystem, many people may think, oh, just it's a technology, it's R&D. Yes, it's important. R&D is important. But there are other things I'm talking about from here, let's say a national perspective. Yes, we need to protect the critical infrastructure. These are the things. It's an ecosystem that needs to be built. It is a R&D base that has to be there. Technology is critical. The process, what are the processes that are followed in these critical infrastructure sectors? The asset owners, are they following sound scientific process to sort of risk assessment process to prevent, or all those things to sort of ensure this infrastructure is secure? Then the people, those who manage these systems or to operate this system, are they sufficiently skilled to sort of not only manage, but the regular users, the operators, they have to be skilled in cybersecurity and all those OT technologies. Then the compliance, are there any regulatory framework wherein minimum cybersecurity enforcement is accomplished or ensured across the sector, so that there is a minimum compliance? Anything beyond minimum compliance, yes, more than the compliance is needed from a cybersecurity point of view, but at least baseline cybersecurity can be established through some kind of compliance kind of process. And of course, industry and university and government labs and others can work as a sort of collaborative way to accomplish this whole thing. So in the interest of time, let me just quickly go through a few more slides. So just to sort of restate what I said, when it comes to energy infrastructure like smart grid cybersecurity is our smart grid security. is basically a union of information security, infrastructure security, the system, control system that manages the grid that needs to be secure as well. Then the physical security of critical assets are extremely important. Somebody can physically go and vandalize or goes to close proximity and create physical damage or have access to those system. Physical security is equally important as well. So the conventional information security properties, confidentiality, integrity, availability, non-repudiation, authenticity, all those properties using encryption, digital signature, those kind of technology are relevant. Again, as I mentioned, grid is a very complex system, different time scale at which control loops and decision making happens. For some control loops and decision making, one could still use heavy duty solutions that are used in the IT security world. But other cases, when there is timing is very critical, operations, control operations are milliseconds, microseconds, those levels, then one needs to have lightweight solution. So one could adapt to the information security solution or tailor it to the grid or OT environment, any critical infrastructure, whether it is a grid or transportation or advanced manufacturing, similar concept applies. Then you have the infrastructure security, the routers and the protocols that are part of the infrastructure, they have to be secure. Again, if you have Cisco routers and or Juniper routers or any routers that are part of this wide area infrastructure, those security of those routers, those infrastructure security solution is definitely valuable and they could be utilized. Then you have what is known as a control system, the system that monitors and controls and protect the operation of the infrastructure itself. In the case of grid, you have generation, transmission, distribution, market, all those things, the control systems, securing them, make them not attack resilient is important. They're like GE, General Electric, or Siemens, or Hitachi, ABB, any of those control system providers, they need to incorporate security into their software and their embedded systems and so on. That is important. Then, of course, the physical security. So you need to sort of have a sort of synergistic defense in depth kind of solution where information security, infrastructure security, control system security, and physical security, they have to coexist to really protect the critical infrastructure in a holistic way. So then just going into a little more detail about risk assessment. Risk is essentially, as I mentioned, that is a very fundamental thing. Before even doing anything in cybersecurity, one needs to understand what are the risks. We are talking about cyber risk. There are other risks, right? There is a hurricane, there is a extreme event of some kind that is coming, what impact it will have on the infrastructure, what is the likelihood and what would be the consequence. So likelihood times the consequence is the risk. So especially for natural events, there are models available. They accurately estimate those risks. What is the likelihood of some major event or natural event occurring? If such an event happen, it will create some damage to some equipment, some portion of the grid or some portion of the critical infrastructure. Because of that, what would be the consequence? So there are models available, reasonably well understood. But when it comes to cyber risk, the definition is likelihood, time, consequence, still the same, but the likelihood happening through a is basically a threat actor. It could be a nation state, or it could be a sort of hacker group or terrorist, whoever it is, a threat actor exploiting a vulnerability in the cyber system. It is a joint probability. What is the likelihood the threat actor, bad actor, exploiting a vulnerability that is there in the cyber in cyber layer or cyber infrastructure of the critical infrastructure? If such exploitation happens, what would be the consequence? That is the impact. So when you multiply those two things, you get a risk. So the problem here is, as you see, the impacts could be load loss like blackout or market impact, equipment damage, There could be various type of impact. The challenge here is modeling the likelihood. In this case, is very challenging. Who are the threat actors? What is their motive? What are the resources they have? When they will target? Why they are targeting? So it is more of an art than a science. So analyzing threat intelligence, threat analysis is more of an art than science. Whereas vulnerability analysis or impact characterization, those are very well understood quantitatively. One can have a mathematical model to analyze, but threat intelligence is not well understood. So that's why a lot of research that are going on. How do you assess threat from a sort of malicious adversary point of view? So just to give even from a broad perspective, risk management process involves risk planning, risk assessment, risk handling, and risk monitoring. So risk planning means you need to have a risk assessment process in place every 6 months or so. You need to do this risk assessment. There is a risk assessment officer. These are the input. This is the output. It comes out. This kind of plan should be in place. Then the risk assessment itself is systematically going through what are the different scenarios and associated with each scenario. What are the consequences? Then you computing those risk indices. That is the risk assessment. Risk assessment itself can be done in a qualitative way or quantitative way. I'll show you in the next slide. So once the risk is assessed, so there is a threshold. If the computed risk is below the threshold, we don't have to worry about the threshold, again defined by the expert who knows the infrastructure. Asset owner, for example, if it is above the acceptable risk level, then the risk has to be mitigated. That is where the risk handling comes. As part of the risk handling, there is an investment analysis needs to be done. You want to optimal investment. That means minimum investment you do to maximize the number of risks that are mitigated, right? You don't want to spend too much, but it is optimal investment decision to maximize the number of risks that are mitigated. So risk handling. Then once the risk is handled, they disappear. That means they are fine. Right now, you don't have any risk that are above the acceptable threshold, but that needs to be continuously monitored. That's where the risk monitoring comes, because the new vulnerability may emerge, new threat actor may emerge, the probability may go up, or the system topology may have changed. Anything, whether in the cyber layer, physical layer, or in the adversary context, things have changed, or vulnerability. There is all of a sudden some zero-day vulnerability being exploited, or some kind of new vulnerability discovered. So it will change the overall risk. Whatever that was acceptable before, all of a sudden become unacceptable. So that's why risk monitoring is a continuous process. Once it is there, that feedback based on those thing, then again one has to do risk assessment and handle those risks. It is an ongoing process. So one has to have a robust process such as this. It is a sort of practical thing. Then there are research things that can be done. How do you assess the risk itself? So there are qualitative risk assessment, like as you see the probability of something happening, and the y-axis very high, medium, and so on. What are the impacts? What do you see on the x-axis? Negligible, marginal, critical, and so on. Then the experts know, you qualitatively ask them, oh, there is a scenario 1, scenario 2, scenario 3. The scenario 1, oh, somebody is now trying to create a major, probe the network. Yeah, very likely, but what is the consequence? Negligible. That is S1. Things like that. So you can enumerate all different comprehensive set of scenarios and map those scenarios into these cells. Depending upon which cell it got mapped into, then you see, oh, there are, let's say, scenario S4 got into a cell that is high risk. That means the probabilities or the likelihood is high, but the consequence is critical. It is high risk. That means anything that is mapped into the red zone, that means needs to be mitigated. So either by reducing the probability from high to medium, that means you come down to this yellow down, or you reduce the consequence from critical to marginal, or you do both to sort of go in a diagonal manner. So one can make these high risk scenarios like S4 by suitable investment in the cyber layer, for example, if you invest, you reduce the probability. That means more the infrastructure is a lot more secure than before because of more investment in the cyber security. Like you could have stronger authentication, higher encryption, or things like anomaly detection on top of just having a firewall and things like that. They can reduce the probability. That is a lot more cheaper compared to you adding another generation unit or another transmission line network. Those are physical resources, a lot more expensive. So one can come up with scenarios and map those scenarios and identify the scenarios that are above the acceptable level, then the threshold, then find out the minimum cost to reduce the risk. This is one way of doing it, and expert, they can do it in a qualitative manner. So that is called qualitative risk assessment. Then the quantitative risk assessment, the problem with qualitative risk assessment is subjective. Each expert they can map a scenario S1, S2 in different cells. It is not verifiable. Of course, you can have ask different experts, then you can merge these results to get a final results. That is a sort of useful thing to do. The other way to do is, can we systematically model the attacker-defender interaction through a game theory kind of model? So that's where if you look at the bottom, attacker characterization, the attacker targeting the cyber network, what are the different attacker objectives and behavior? They can be sort of posed as a game theory kind of formulation. Then what kind of impacts they can have. Similarly, from a defender point of view, defender has certain objective and behavior, attacker has certain objective and behavior. It's a game between attacker and defender that is modeled as a game theoretic formulation, as you see from bottom up in this diagram. Then based on that, one can come up with what are those risks, and based on which what risk mitigation in an optimal investment defense strategies one can do in the cyber network, on the physical network. So these kind of models are gaining importance to models adversaries who are sophisticated. It also lays out what are the different ways in which the attacker can perform different the strategies the player adversary player can do. You sort of emulate that process to figure out what is the best course of action one can do as part of this game theoretic formulation. That way, the risk assessment, what I call threat intelligence, is more of an art. You're moving that from art to a sort of scientific process by using game theory type of model. These are still more of research, academic research than industrial practice. What I showed before, the qualitative risk assessment is more of industrial practice, even though it is subjective, whereas the game theory type of formulation, a lot of assumptions are being made, but is scientifically elegant, but still these have to be validated. They are still mostly in the academic arena, not in industry practice yet. So some of the other technologies from a solution point of view, one is moving target defense. So this is a way to, let's say, a substation and control center or two endpoints. They are communicating. Adversary is trying to disrupt that communication between client and server, right? Or some client talking to a server in the cloud, or it doesn't matter, two endpoints or two machine-to-machine communication. So how do you sort of protect that communication channel? Or the one example I'm talking about communication channel, it could be broadly a system as a whole. One can introduce controlled uncertainty rather than just one example. The two endpoints are talking, they have IP address, internet protocol address, IP address. So the adversary knows what is the IP addresses they are talking to. Sender IP address, receiver IP address. So they can send a, let's say, denial of service attack or other type of attack. They can target those IP address to sort of overcome such kind of an attack or prevent such kind of attack. The system can introduce controlled uncertainty in the operation without any adverse effect. That means you confuse the adversary by changing the IP address rapidly, so that they don't know what is the IP address you are using, but these two endpoints, they know what their IP address randomly they are using, but they have a pre-agreed random sequence based on which they are changing the random number. Again, they have a pool of address, but they change within that pool at a given point in time, they are using one address, but they will keep changing those address. They know based on predetermined random sequencing what is the next IP address, but the adversary doesn't know. So this is one example. It's called IP hopping. You keep hopping the IP address in a randomized manner so that the adversary doesn't know what the IP address these two endpoints are communicating. That way one can prevent this kind of attack. So this moving target defense, I just mentioned about IP hopping, but it could be applicable to measurements. You take measurements in a grid or other critical infrastructure, you take a lot more measurements than needed. Only a subset of those measurements utilized for doing state estimation or any kind of analysis. But which subset that is going to be used is a random subset. That random subset keeps changing every time. The adversary doesn't know which random subset is going to be used. So if they go and corrupt one measurement or two measurement or one control or two control, it may not necessarily impact because the random subset that is going to be used may not include these corrupted measurements or corrupted control. So the key for moving target defense algorithm to work, one needs to have enough redundancy in the IP address or in the measurements, in the control signal, whatever it is, enough redundancy should be there. Within that redundancy, one needs to do what is known as randomization. Redundancy and randomization are the two key principles to achieve moving target defense in networks or systems. And these have been widely attempted. There are some technology solutions are there, prototype deployments are there. But the challenge here also, they introduce a lot of overhead. While you introduce controlled uncertainty, if it leads to some adverse effect on system operation, it increases the latency or it sort of results in packets getting dropped, critical measurements getting dropped. That is not acceptable. So one needs to make sure these solutions are feasible. At the same time, they are able to achieve this prevention of these attacks. This has a lot of promise, and several work that exist, especially IP hopping, port hopping, those kind of things in the IT kind of network. But how do you sort of adapt such solution to industrial control systems and cyber physical system? There is a lot more work needs to be done. So just to wrap up quickly, from a cyber physical control system point of view, you have a cyber system, physical system. There is a wide area communication in the middle, sensing measurements, sensing signals go through the wide area communication network. It could be subject to different kind of attack. Then similarly, the cyber system makes some decision, then it controls the physical system. The control signals could be attacked, sensing could be under attack, control could be attacked. There are so many measurements, sensing measurements, so many control signals, and there are so many control loops, not just one control loop. There's so many control loops depending upon the infrastructure that you have, and each control loop has its own timing properties and so on. The attacks, as I mentioned, it could be man in the middle attack, data integrity, denial of service, timing, replay, and so on. So again, the other useful concept to think about when you think about cyber physical or smart grid, this kind of thing, there are two sort of subsystems, cyber and physical. They are interdependent manner integrated. In a normal state is some kind of state diagram notion. Cyber and power subsystems, they are in normal states. If there is an attack happen, there is a kind of pre-alert state. That is where the cyber is in alert. There is being some attack being targeted, but grid physical system, there is no real any effect or any kind. But pre-alert to actual alert states, that means there is actually some compromise happen in the cyber layer. Physical layer is still fine, but when there is actual from alert state to compromise state, that is where the attack in fact actually caused the physical system have some kind of malfunction, system become unstable. So you have a normal state to pre-alert to alert and compromise state. These are the kind of transition. But if when you are in pre-alert state in the top, if there are some prevention techniques, it's able to prevent, like moving target defense I talked about, or other kind of technologies, then one can directly get into the normal state. The pre-alert never becomes an alert state. Similarly, from an alert state, there are anomaly detection or intrusion detection. They are able to detect and able to cyber mitigation. They can go to normal state right away without leading the system get into unstable or compromised state. So same way. So once it is compromised, then there could be cyber and physical mitigation, because there is something compromised. Physical system reconfiguration, controlled islanding, and other kind of physical infrastructure changes, especially in the grid. Similar concept exists, reconfiguration underlying physical system, or isolation of affected components, and so on. Those things can happen in the physical and cyber layer to bring the system back to a operational state. So it's kind of a useful notion to think about what attack can cause from a system state diagram point of view, and how do you steer the system to back to normal state by invoking different cybersecurity solution, whether it is the prevention or detection, mitigation, and resiliency kind of techniques. So again, just bring back the anomaly detection and attack mitigation. If those two are there in an integrated manner, you could call one definition is attack resilience. Attack resilient control system have inherently anomaly detection and attack mitigation. For anomaly detection, one could have model-based or rule-based or machine learning-based, or combination of things. They could be utilized for anomaly detection and also attack mitigation. There is a lot of ongoing research leveraging machine learning and using a data-driven approach for building anomaly detection, also coupling with model-based, because these underlying systems have physical or characteristics based on the physics of system operation that could be leveraged. So there is a lot of opportunity for hybrid type of anomaly detection and model-based and hybrid attack mitigation to make this overall system, control system, attack resilience. As I said, complex infrastructure like energy infrastructure, power grid, they have a lot of control loops. Each one of them, whether it is a distribution control system or a generation control system or transmission control system, there are different control systems. Each one of them, the different variations of techniques could be adapted to make them secure. So finally, just before I wrap up, in academic research or even industry research, test beds are important to sort of test and evaluate different cybersecurity solutions, inject attacks, and see what consequences they have on instrument defenses, to see how effective they are. One is now going and deploying and seeing the real infrastructure, but that is very expensive. You don't want to wage an attack on a real infrastructure and see what consequences, whether those attacks are detected or mitigated. Instead, those things have to be tried out in a test bed, or even yesterday's talk. I think there was a mention by one of the speakers about digital twin kind of notion. Digital twin or test bed, what we are talking about, you have a lab scale infrastructure that emulates simulation, emulation, and some real components. They can be integrated to provide a realistic platform or digital twin or testbed infrastructure wherein one can create attack defense exercise and study different solutions. So one way to sort of architecture such digital twin testbed is, okay, you have physical layer, that's where now all the real power system, generation, transmission, all those distribution, all those things comes in. That's probably one could have a simulator, real-time simulators. Those could be utilized for that. The communication layer, real protocols and DNP3, Modbus, or any protocol of that kind, Icicc. Those protocols, one could have real protocol. It doesn't need to be simulation. Information and control layer, you could have real energy management system, distribution management system, those software, control software, depending upon the type of things you build. It could be simulation or it could be real, depending upon the resource and the fidelity of experimentation and realism of the experimentation that needs to be done. So one could have three layers of abstraction, could be more layers of abstraction. This is one kind of abstraction where three layers are there and well-defined interfaces between these layers. One can build a CPS security test bed or digital twin test bed. Then within this test bed, the attacks can be on the communication layer or information control layer. This is essentially on the cyber. We are talking about cyber attack. Similarly, the defenses could be instrumented on those layer to see how they are, how effective they are. So one can utilize this kind of test bed for cyber defense exercise. So we have built such a digital twin test bed at Iowa State, mimicking real grid environment with a lot of substation, with the power system simulator, real-time simulators, then the control center on the right, in between wide area communication emulator. So you create a control center, wide area communications with a lot of substation talking to the control center. Then the substation in turn have no relays and phaser measurement units. They in turn connected to real-time power system. So it is a simulation, emulation and physical devices, real protocols. So one can inject attacks like the one I was talking about, timing attack, measurement attack, replay attack, denial of service attack on the wide area communication or the substation. Then the impact will be felt in the overall system operation, and how do you mitigate? A lot of studies can be done. We have done a lot of studies on vulnerability assessment on real protocols, real controllers, real devices, industry-grade platform. We found vulnerabilities, we responsibly reported them to authorities. Then risk assessment and risk mitigation kind of studies. You create various attack vectors, so different scenarios, and see what impacts they have. Of course, we have to have some probabilities externally to the test bed. Then you multiply those probabilities with the impact, you can compute those risks. So risk assessment, then you also instrument some defenses and see how risk is mitigated. So it could be utilized for risk assessment and mitigation. Then a more advanced complex attack defense evaluation of control system, like wide area protection, wide area control, wide area monitoring kind of application, to sort of create situation that have cascading kind of flavor, one event causing another event causing multiple secondary events causing even more tertiary events. So the cascading nature of grid operation with the cyber physical interaction can be simulated and emulated within this environment, and one can study the stability, reliability, the overall grid characteristics, stable operation can be studied. So the several studies we have done using those test bed. What I shown before, the bottom, what you see here with those bulbs and so on, is the actual physical infrastructure with servers and real-time digital simulator, relays, phaser measurement units, all those things integrated with the substation, industry-grade substation, industry-grade control center, all those things. The cyber layer is real, the physical layer is simulated. That's what in this infrastructure we architected. So then there are a lot of standards, as I mentioned before, for a sort of robust cybersecurity ecosystem. It is not just technology and people, it is about process, it is also about compliance. NERC is the North American Electric Reliability Corporation Critical Infrastructure Protection compliance standards. Its objective is physical, cyber, operational, and supply chain security for the bulk power system. It has been there more than 10 years. It's widely implemented for the bulk power system in North America. Similar kind of regulations or compliance program is in place in other parts of the world. I'm sure in India also similar things are being followed in terms of best practices to protect the critical infrastructure, in particular the energy sector. So there are a lot of aspects to it. As I said, physical security, cyber security, the operational aspect of security, especially for bulk power systems, supply chain security. So different things, including protecting sensitive data, everything, and threat response, incident response, vulnerability assessment, patch management. There are like 14 or 15 SIP criteria, SIP 001 through 14 criteria that focus on different aspects. Those are all there. Then the NIST cybersecurity framework, it is not a compliance standard, but it's a framework. It kind of enables to develop further standards or compliance process so that everyone understand what is the baseline expectation for these systems. So basically, the sort of life cycle model I showed, like deterrence, prevention, detection, mitigation, resilience, and attribution. Similar to that, they have identified 5 steps, key steps: identify, protect, detect, respond, and recover. Somewhat similar to what I said, but they also emphasize risk-based approach for cybersecurity, extremely important. Then, of course, they talk about collaboration. I mean, this framework was developed with the collaboration between industry and public sector and academia and government. So then they also have what is known as capability maturity model with respect to different criteria or process. Let's say risk assessment is one important domain as part of this NIST cybersecurity framework. Whether the risk assessment, what level of implementation, it is maturity level 1 through 4. 1 means it's partially implemented. That means risk assessment process is in place, but it's ad hoc, partially implemented. Or number 2, that means risk informed. Okay, they make some decision based on the risk, but whether this process is repeatable, probably not. If it is that is the case, it is 2. If it is a little more matured, it's a repeatable risk assessment process, 3. Then number 4, it's adaptive. The risk assessment process itself is adaptive to changing requirements. It's a lot more matured. So there are different domains. Domains means different key domains, whether risk assessment or vulnerability assessment or threat assessment. There are different kind of educating workforce and so on. There are different domains are there. They identified as part of the CSF framework. For each domain, what is the level of implementation tier, 1, 2, 3, or 4. So depending upon that, one can sort of do a self-assessment of risk. There is also DOE has C2M2 cybersecurity capability maturity model. C2M2 is a similar kind of framework. Again, it has several domains, 7 or 8 domains. For each domain, different tiers are there. Then one can do a self-assessment to see where that particular organization or particular set owner with respect to cybersecurity readiness and preparedness, one can do a self-assessment or maturity level in general. So the last 1 or 2 slide, I just want to quickly say, cybersecurity for IoT is a big area. IoT is in the Internet of Things. I'm sure you heard multiple times. Some of you are also working these kind of areas. But smart agriculture, a lot of sensors, whether it is a crop or animal and other places. In Indian context, it may not be yet fully advanced to automation perspective, the agriculture sector. It is labor intensive, but more likely more automation will happen in the agriculture also, smart agriculture. A lot of sensors, and they go through different gateways to the cloud and various analytics that happens in the cloud. The data security, data privacy is important. Then real-time decision making happen. This IoT enabled smart agriculture or IoT enabled smart manufacturing or IoT enabled smart transportation, whatever that may be, you just replace on the left, instead of agriculture to manufacturing or agriculture to transportation. This IoT framework still holds. It is susceptible to different type of attacks, data attacks, network type of attacks, supply chain attacks, or other relevant attacks. They need to be secure as well. So again, this is just to show a little more detail about different layers and what happens in the smart agriculture at the physical layer, edge layer. Physical means the sensors and the plant and other things, the physical layer, this is the edge layer, then the cloud layer. So what are the different analytics, what kind of decisions that are made, what kind of sensing and control that is happening, but they are all susceptible to attacks. More automation means more opportunity for more attack surface as well. So these have to be systematically analyzed, and those whatever the attack surface has to be systematically reduced as well. So just to conclude, attack surface is continuously increasing in all these critical infrastructure sectors as more and more digitization happening in this infrastructure. They become more and more cyber physical or cyber enabled IoT type infrastructure. So attack surface has to be systematically analyzed, and systematically it has to be reduced. That is important. Adversaries have become more and more sophisticated, as I mentioned before. Earlier, no cyber attacks on critical infrastructure used to be a low frequency, high impact event, but low frequent events. But there are no more low frequent events. More and more events are happening in recent years. The threat landscape dynamically changing, so there are no more low frequent events. They are frequently occurring events. Attack frequency and stealthiness are likely to increase. That is a worrying trend. Robust cybersecurity, as I mentioned, technology, process, people, compliance, all are important as part of your cybersecurity ecosystem. Compliance only provides a baseline security. One needs to go much beyond the compliance, but sort of across industries, across different sectors. Even within the same sector, all companies follow certain minimum compliance, means baseline security is provided depending upon the resources and threat, risk profile. One could have additional security features. So risk-based approach is cybersecurity investment is pragmatic. That means when you do cybersecurity investment, it's risk-based or risk-informed, as opposed to not just investing resources in a dark manner. Model-driven and data-driven cybersecurity solutions are promising. As I said, in a critical infrastructure, they rely on cyber physical system operation. There are underlying physical process involved. Model-driven approaches, they are very useful, and relying on data sets and a lot of data-driven solutions, machine learning, those kind of things, coupled with the model-driven, it is a promising approach for anomaly detection, attack mitigation, those kind of cybersecurity solutions. Skilled workforce is extremely important for R&D and education, and many of your faculty members, I'm sure, educating students, current and next generation students, with cybersecurity skills, not just in theory, but also practical skills, hands-on learning. Those things are extremely important for skilled workforce for the industry and for the society. So that's my last slide. Just I would like to thank all of you for listening to my talk, and I would like to also acknowledge some of the funding sources, U.S. National Science Foundation, U.S. Department of Energy, and some of the research center, industry, university research centers that Iowa State is part of it. They have funded this project over the years. I would like to acknowledge their support for some of the work that I have presented. Thank you so much. If you have any question, I would be happy to answer.
Yes, thank you, sir. Sir, there is one question from one of our attendants, Dr. Pramod. I will read out the question to you. What is your view of using quantum algorithms for cybersecurity, say for game theory?
Yeah, I would say I'm not an expert in quantum, but it's a promising area. I would suggest there are a lot of effort that has been going on within, let's say, Department of Energy, especially in the area of quantum cryptographic solution, There are several projects, some companies, they were building some kind of prototypes to showcase what is the feasibility and what is possible and so on. I would suggest you to look at Department of Energy, DOE. I mean, if you say quantum, crypto, or they have fact sheets on different projects that are funded, you will find more than one project focusing on quantum and security, quantum cryptography, those kind of things. Personally, I'm not expert on quantum itself, but I do see there is a lot of promise in quantum computing, how it applies to cybersecurity. There are efforts, as I mentioned, within DOE to explore those kind of frontier research, but they are not anywhere close to being actually deployed at this point, based on what I know. Thank you.
Thank you, sir. Participants, if you have any more questions, you may please go ahead and ask. Okay, thank you, sir, for the excellent and resourceful deliverance of innovative and empowering talk. We are delighted with your words. With this, we come to the end of the keynote sessions for the day. Thank you, sir. Thanks a lot. Now,
Thank you so much. I really appreciate the opportunity. Thank you.
Now, I would like to request participants to join the respective tracks for the paper presentation.